I'm so glad you found your way here. Right now, as you breathe, time is flowing through you at about 186,000 miles per second, the speed at which space-time itself moves. You'll discover how the clock of the universe started ticking in the first unimaginable fraction of a second, and understand why every moment you experience is a gift from that ancient cosmic dawn. Welcome to Get Sleepy Science. Wherever you are right now, perhaps feeling the weight of this day settling into your body, or watching shadows lengthen across your walls, allow yourself to rest in this present moment. We'll drift through 100 space facts about time's mysterious beginning, from the impossible instant when nothing became everything, to the first tick of cosmic clocks, to the river of moments that flows through your life right now. These quiet journeys through space create a cosmic community of peaceful minds. Feel free to like and subscribe, or share a thought down in the comments. It helps others find their way here too, one sleepy soul at a time. It means the universe to us. Settle deeper into your pillows now. Let your shoulders drop, your breathing slow and steady. You don't need to hold on to any of this cosmic knowledge. Just feel that peaceful heaviness spreading through you, like you're floating weightless in the vast, silent darkness between stars, drifting gently towards sleep. Close your eyes and breathe deeply. You're floating where starlight paints pathways through infinite space. Let your mind drift with cosmic silence. And now we begin. Time began 13.8 billion years ago with the Big Bang. This comes from careful measurements, observations confirmed by the Atacama Cosmology Telescope and James Webb Space Telescope in 2025. Before this moment, there was no before. No ticking clocks, no passing seconds, no yesterday or tomorrow. The universe and time were born together, like twins emerging from nothing. Scientists measure this age by observing the cosmic microwave background radiation, the afterglow of creation itself, which still fills space today at a temperature of 2.725 degrees above absolute zero. This ancient light traveled more than 13 billion years to reach us, carrying encoded information about the universe's first moments. The precision of this measurement has improved dramatically in recent years, narrowing the uncertainty to just 21 million years, a tiny fraction of cosmic time. The concept of time itself is stranger than most people realize. According to Einstein's theory of relativity, which has been tested thousands of times and never failed, time is not separate from space. They form a single fabric called spacetime. This means time can bend, stretch, and even slow down depending on gravity and motion. Near massive objects like black holes, time moves more slowly than it does here on Earth. Astronauts on the International Space Station age slightly slower than people on the ground, just a few milliseconds over months, but measurable with atomic clocks. Time is not the rigid, universal clockwork that Newton imagined. It's flexible, relative, and deeply connected to the shape of the universe itself. Understanding this helps us grasp how time could have a beginning at all. For most of human history, people believed time had no beginning. Ancient Greek philosophers imagined an eternal cosmos, cycling through endless creation and destruction. Medieval theologians debated whether God existed outside of time or within it. Even Einstein initially resisted the idea of a universe with a birthday, preferring a static, eternal cosmos. In 1929, astronomer Edwin Hubble discovered that distant galaxies are moving away from us in all directions. The farther away a galaxy is, the faster it recedes. This observation, confirmed by thousands of measurements since, meant the universe is expanding. If you run this expansion backward in time, like rewinding a movie, everything converges to a single point. Belgian physicist Georges Lemaitre called this the primeval atom, what we now call the Big Bang, the moment when time itself switched on. The Big Bang was not an explosion in space. It was an explosion of space itself. There was no empty void where the explosion happened. Space, time, matter, and energy all emerged together from a state we still don't fully understand. Imagine every point in the universe expanding outward simultaneously, like dots on the surface of an inflating balloon. The balloon itself represents space growing larger, carrying galaxies along with it. This expansion continues today. The James Webb Space Telescope, launched in 2021, observes galaxies so distant their light has been traveling for over 13 billion years. These galaxies appear as they were when the universe was less than 500 million years old, cosmic infants, caught in a moment of violent star formation, their light stretched red by the expansion of space-time itself during its long journey to our eyes. Before the Big Bang, asking what came before may be meaningless. Time itself didn't exist yet, so there was no before in the way we understand it. Imagine trying to travel north of the North Pole. The question doesn't make sense because north ceases to exist at that point. Similarly, time begins with the Big Bang, and asking what came earlier is like asking what's north of north. Some theories suggest time might be cyclical, with universes expanding and collapsing in an eternal sequence. Others propose that our universe is one bubble in an infinite multiverse, where time runs differently in each bubble. The truth is, we don't know what lies beyond the boundary of our cosmic timeline. And that not knowing is part of the profound mystery at the heart of existence. The earliest moment of time we can describe scientifically is called the Planck epoch, lasting from time 0 to 10 to the power of -43 seconds after the Big Bang. That's a decimal point followed by 42 zeros and then a 5. This is the Planck time, named after physicist Max Planck, who first calculated it in 1899. At this scale, smaller than any distance we can measure, our understanding of physics breaks down completely. Both quantum mechanics, which describes the very small, and general relativity, which describes gravity and space-time, must apply simultaneously. But these two theories are incompatible at such extreme conditions. We need a theory of quantum gravity, which scientists have pursued for decades but haven't yet achieved, to understand what happened in that first infinitesimal moment when time began its flow. During the Planck epoch, the universe was unimaginably hot and dense. The temperature reached 10 to the power of 32 degrees Kelvin, a number so vast it's hard to comprehend. All four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single force. Space itself was churning with quantum fluctuations so violent that the concepts of distance and duration lost their meaning. According to 2025 research by theoretical physicists at multiple universities, space-time at this scale may have been granular or foam-like rather than smooth, with tiny bubbles of space and time constantly appearing and vanishing. This quantum foam represents the smallest possible texture of reality. Below the Planck scale, space and time, as we know them, simply do not exist in any recognizable form. The Planck length is approximately 1.6 times 10 to the power of -35 meters, far smaller than an atom, smaller than a proton, smaller than anything we can directly observe. To give perspective, if you expanded an atom to the size of the observable universe, the Planck length would still be smaller than a single tree on Earth. At this scale, gravity becomes as strong as the other forces. Attempting to measure anything smaller than a Planck length would require so much energy that the energy itself would collapse into a black hole, making the measurement impossible. This sets a fundamental limit on how precisely we can know the universe's structure. The Planck time, the time it takes light to travel one Planck length, is 5.39 times 10 to the power of negative 44 seconds. This is likely the shortest meaningful interval of time in our universe, the first tick of the cosmic clock. After the Planck epoch, the universe entered what cosmologists call the Grand Unification epoch, lasting until about 10 to the power of negative 36 seconds after the Big Bang. During this brief window, the universe cooled enough, though still at 10 to the power of 27 Kelvin, for gravity to separate from the other three forces, which remained unified. Think of it like water freezing. As temperature drops, the properties of matter change suddenly. This separation of forces may have released enormous energy, triggering a period of exponential expansion called cosmic inflation. In less than a trillionth of a second, the universe grew from smaller than an atom to perhaps the size of a grapefruit, smoothing out irregularities and setting the stage for everything that followed. This theory, proposed in 1980 and refined ever since, explains why the universe appears so uniform in all directions. So yes, time did begin, and it began in the most dramatic way imaginable, not with a gentle sunrise, but with an explosive emergence from quantum uncertainty. The first 10 to the power of negative 43 seconds saw time itself stuttering into existence, space-time condensing from pure energy, the universe smaller than the smallest particle, yet containing everything that would ever be. But this raises profound questions. If time had a beginning, what determined when the beginning would begin? Can an event cause itself? Philosophers and physicists grapple with these paradoxes, finding no easy answers. What we know for certain is that observable time, measurable time, the time that governs our lives and thoughts and breaths, started 13.8 billion years ago in a flash of incomprehensible power. The mystery of why remains. The period of cosmic inflation, occurring between 10 to the power of negative 36 and 10 to the power of negative 32 seconds after the Big Bang, solved several puzzles that had troubled cosmologists. Before inflation theory, scientists couldn't explain why the universe looks almost identical in every direction. Regions of space too far apart to have ever exchanged light somehow have the same temperature and density. Inflation solves this by proposing that all these regions were once close together, then inflated apart faster than light could travel. Space itself expanded, not matter moving through space, so no speed limit was violated. During inflation, the universe grew by a factor of at least 10 to the power of 26. Imagine a marble swelling to larger than the observable universe in less time than it takes light to cross an atom. Measurements from the Planck satellite in 2018 and updated analyses in 2024 confirm this theory's predictions with remarkable precision. The James Webb Space Telescope, which began observations in 2022, has revolutionized our understanding of cosmic time by peering deeper into the past than ever before. In 2024 and 2025, JWST discovered galaxies that formed just 300 to 400 million years after the Big Bang, infants in cosmic terms. These galaxies appear surprisingly bright and structured, challenging previous models that predicted they would be smaller and dimmer. One galaxy, designated JADES-G S-Z14-0 and observed when the universe was only 290 million years old, already contains mass equivalent to hundreds of millions of suns, organized into bright clumps and regions of intense star formation. These early galaxies appear messy and turbulent, not yet settled into the elegant spiral structures we see in later cosmic epochs. This suggests that galaxy formation began even earlier than scientists thought, possibly during the universe's first 100 to 200 million years. Time flows differently depending on where you are in the universe. On Earth's surface, time moves slightly slower than it does at higher altitudes because Earth's gravity warps spacetime. GPS satellites, orbiting 12,500 miles above, must account for this time dilation. Their clocks run about 38 microseconds faster per day than clocks on the ground. After just one day without correction, GPS would be off by several miles. This effect, predicted by Einstein and confirmed countless times, means that astronauts aboard the International Space Station age differently than people on Earth. During a 6-month mission, an astronaut might age about 0.007 seconds less than someone on the surface. These tiny differences accumulate. If you lived your entire life at the top of Mount Everest, you would age about 15 milliseconds more than someone at sea level. The cosmic microwave background radiation, discovered accidentally in 1965 by Arno Penzias and Robert Wilson, is the oldest light we can see. This faint glow fills all of space, a relic from 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. Before this moment, the universe was opaque, a dense fog of plasma where photons scattered constantly off free electrons. When atoms finally formed, photons were released in all directions, creating a flash of light that has been traveling through space ever since, stretched into microwaves by cosmic expansion. New measurements from the Atacama Cosmology Telescope in 2025 have provided the highest resolution images yet of this background radiation, revealing details about density fluctuations that would eventually grow into galaxies, stars, and planets, including the one you're resting on right now. In the first 3 minutes after the Big Bang, the universe was a cauldron of nuclear reactions. At temperatures around 1 billion Kelvin, protons and neutrons fused together to form the nuclei of light elements, hydrogen, helium, and traces of lithium and beryllium. This process, called Big Bang nucleosynthesis, created the cosmic recipe that persists today. About 75% of ordinary matter became hydrogen, 25% helium, with tiny amounts of other light elements. All heavier elements, the carbon in your body, the oxygen you breathe, the iron in your blood, were forged later inside stars. The precise ratios of hydrogen to helium, measured in ancient gas clouds, match theoretical predictions with stunning accuracy, providing powerful evidence that our model of the early universe is correct. Those first 3 minutes determined the chemical composition of everything that would ever exist in the cosmos. For the first 380,000 years, time moved through a universe you couldn't have seen. The cosmos was filled with a hot plasma of electrons, protons, and photons, all colliding constantly. Any light emitted scattered immediately, making the universe opaque like thick fog. This era, called the photon epoch, was a time when radiation dominated over matter. The temperature slowly dropped as space expanded, cooling from billions of degrees to thousands, like a furnace gradually losing heat. Then, at a temperature of about 3,000 Kelvin, something remarkable happened. Electrons combined with atomic nuclei to form the first stable atoms. This event, called recombination, made the universe transparent for the first time. Light could suddenly travel freely, and that released light, stretched and cooled over billions of years, is what we detect as the cosmic microwave background today, a photograph of the infant universe. The universe's first era, without light, is called the Cosmic Dark Ages, lasting from 380,000 years to about 150 million years after the Big Bang. During this long twilight, no stars yet existed. Space contained only neutral hydrogen and helium gas, dark matter clumping in invisible filaments, and the fading glow of the cosmic microwave background. gravity slowly pulled gas into denser and denser clouds. The universe was silent, cold, and utterly dark, a vast emptiness waiting for illumination. Then, gradually, pockets of gas grew dense enough to ignite. The first stars blazed to life, massive and blue-white, burning fiercely and dying quickly. These earliest stars, made only of hydrogen and helium without heavier elements, have never been directly observed. The James Webb Space Telescope is searching for their faint traces in the most distant reaches of space, hoping to glimpse the moment when time moved from darkness into light. Time's passage can be measured by decay. Radioactive isotopes break down at precise rates. Uranium-238 has a half-life of 4.5 billion years, carbon-14 about 5,730 years. By measuring the ratio of parent-to-daughter isotopes in rocks and meteorites, scientists can determine ages with remarkable accuracy. The oldest rocks on Earth are about 4 billion years old, but meteorites date to 4.567 billion years, marking the formation of our solar system. Moon rocks brought back by Apollo astronauts show similar ages. The oldest known star in our cosmic neighborhood, designated HD 140283 and nicknamed Methuselah, initially appeared to be about 14.5 billion years old, older than the universe itself, which puzzled astronomers. Refined measurements, accounting for uncertainties in distance and composition, revised its age to approximately 13.7 billion years, resolving the paradox. This ancient star formed shortly after the Big Bang, carrying the chemical fingerprint of the universe's first stellar generation. The expansion of the universe is accelerating. This discovery, made in 1998 by two teams observing distant supernovae, shocked the scientific world and led to a Nobel Prize. Galaxies are not just moving away from us, they're moving away faster and faster over time. Something is pushing the universe outward against the inward pull of gravity. Scientists call this mysterious force dark energy, and it makes up about 68% of the universe's total energy content. We don't know what dark energy is, whether it's a property of space itself, a new force, or something else entirely, but its effect on time is profound. Eventually, billions of years from now, galaxies will recede so fast that light from them can no longer reach us. The observable universe will shrink. Distant future civilizations might see only their own galaxy, lonely in empty blackness, with no evidence that a wider cosmos ever existed. The Atacama Cosmology Telescope in Chile released new data in March 2025, providing the clearest images yet of the cosmic microwave background. Combined with data from the Planck satellite and the South Pole telescope, these measurements refined our estimate of the universe's age to 13.797 billion years, with an uncertainty of only 21 million years. They also measured the Hubble constant, the rate of cosmic expansion, at 67.4 kilometers per second per megaparsec. This means that for every 3.26 million light-years of distance, space is expanding at 67.4 kilometers per second. However, measurements made using other methods, particularly observations of nearby supernovae, give a slightly higher value, around 73. This disagreement, called the Hubble tension, is one of cosmology's biggest current mysteries. It might indicate new physics beyond our current understanding, or subtle errors in measurement, or perhaps that the universe's expansion rate has changed over time in unexpected ways. At around 150 to 250 million years after the Big Bang, the first stars ignited. These population 3 stars, as they're called, were giants, perhaps 100 to 300 times more massive than our Sun, made purely of hydrogen and helium. They burned incredibly hot and bright, living only a few million years before exploding as supernovae. When they died, they scattered heavier elements into space: carbon, oxygen, nitrogen, silicon, iron. These elements seeded the next generation of stars and planets. The James Webb Space Telescope continues searching for population 3 stars or their remnants. By 2025, researchers have identified several intriguing candidates, extremely distant, faint objects, with spectra that might indicate pure hydrogen-helium composition. None are yet confirmed, but each new observation brings us closer to glimpsing the universe's first stars, whose light has traveled more than 13 billion years to reach us. Black holes warp time more dramatically than anything else in the universe. Near a black hole's event horizon, the point of no return, time appears to slow from an outside observer's perspective. If you watched a clock fall toward a black hole, you'd see it tick slower and slower, eventually appearing to freeze at the horizon, though it would still be falling from its own reference frame. Inside the event horizon, space-time becomes so twisted that the usual rules break down entirely. At the center lies the singularity, a point where curvature becomes infinite, and our equations can no longer describe what happens. Supermassive black holes, millions to billions of times more massive than the Sun, lurk at the centers of most galaxies, including our Milky Way. The one in our galaxy, called Sagittarius A star, has a mass of about 4 million suns and warps space-time across light years. The concept of now is more complicated than it seems. When you look at the Moon, you're seeing it as it was 1.3 seconds ago, the time light takes to travel from there to here. The Sun appears as it was 8 minutes ago. The nearest star, Proxima Centauri, shows itself as it was 4.24 years in the past. Distant galaxies reveal ancient history. A galaxy 10 billion light-years away appears as it did when the universe was only a quarter of its current age. In a sense, there is no universal now binding the cosmos together. Different parts of the universe exist in different time frames, connected only by light slowly crossing the void. Your present moment is unique to your location in space-time. Simultaneity, the idea that events happen at the same time, only makes sense locally. On cosmic scales, time itself becomes fragmented and relative. Time can theoretically be created or destroyed at quantum scales. In particle physics, virtual particles constantly pop into existence from the quantum vacuum, borrowing energy from empty space for infinitesimally brief moments before vanishing. These fluctuations, predicted by quantum field theory and confirmed through experiments like the Casimir effect, suggest that even nothing is intensely active. Some physicists speculate that time itself might emerge from quantum entanglement, the mysterious connection between particles across space. In this view, time isn't fundamental but arises from deeper quantum relationships. Research published in 2024 explored this idea using quantum information theory, suggesting that time's arrow, the fact that it flows forward, not backward, might result from the universe's quantum complexity increasing. The mathematics is dense and speculative, but it opens the possibility that time is not a backdrop for events, but something constructed by the universe's quantum nature. So we've traveled from the first impossible instant to the slow unfolding of cosmic ages. We've seen how time emerged from quantum foam, how it bent near black holes, how it flows differently across the universe. We've learned that time isn't universal or absolute, but flexible and relative, shaped by gravity and motion. The question, how did time begin, has partial answers, but no complete one. Physics breaks down at the Planck epoch. We have equations, observations, measurements, but also mystery. And perhaps mystery is fitting. Time is the medium of our existence, the river we can never leave, the current carrying us from moment to moment. To understand its beginning is to approach the deepest question of all. Why is there something rather than nothing? Why does anything exist? Let those questions drift now, like leaves on water, as we continue gently into deeper knowledge. Take a deep breath and feel this. Every atom in your body, the carbon, the nitrogen, the oxygen, the iron, was created in the core of a dying star. The spacecraft we build, the astronauts we send to the heavens, all made from the material of the universe, returning to the universe. Feel yourself carrying the trace of ancient stars. Every breath you take, you're breathing the same air that astronauts breathed, while looking down at Earth from above. We are all space travelers, flying on a small planet through the galaxy. Now we continue. Around 1 billion years after the Big Bang, the universe entered what astronomers call the epoch of reionization. The first stars and galaxies emitted intense ultraviolet radiation that reionized the neutral hydrogen filling space, turning the universe transparent to light permanently. This transition, studied extensively by the James Webb Space Telescope in 2024 and 2025, happened gradually over several 100 million years. Observations of distant galaxies show this process was patchy, with bubbles of ionized gas growing and merging. By 1.2 billion years after the Big Bang, reionization was nearly complete. The universe had gone from opaque to transparent, from dark to illuminated, from simple to increasingly complex. Time's passage was now marked by light itself, photons streaming freely through clear space, carrying information about star formation and galactic evolution across billions of years. Gravity isn't just a force pulling objects together, it's the curvature of space-time caused by mass and energy. Einstein showed this in 1915 with his theory of general relativity, imagining space-time as a flexible fabric that bends under weight. A massive object like the Sun creates a depression in this fabric, and planets orbit because they're following the curved paths through warped space-time. This curvature affects time as well as space. Measurements confirm this with incredible precision. Atomic clocks at different heights tick at slightly different rates. On Earth's surface, clocks run at a different pace than at mountain peaks. Near a neutron star, where gravity is billions of times stronger than Earth's, this effect becomes extreme. This warping of time by mass and energy is fundamental to understanding how time began with the Big Bang, the ultimate gravitational event. The universe has a temperature, currently 2.725 Kelvin, about minus 454 degrees Fahrenheit, just a few degrees above absolute zero. This is the temperature of the cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space. Measurements taken in 2025, using molecular absorption lines in distant gas clouds, confirmed that this temperature was higher in the past, exactly as predicted. At a redshift of 0.89, corresponding to when the universe was about half its current age, the temperature measured 5.13 Kelvin. This matches theoretical predictions perfectly, supporting the idea that the universe cools as it expands. Going backward in time, temperatures rise. 380,000 years after the Big Bang, the temperature was 3,000 Kelvin. At 1 second, it was 10 billion Kelvin. At the Planck epoch, it exceeded 10 to the power of 32 Kelvin. Time's arrow is also a temperature gradient, flowing from inconceivable heat toward ultimate cold. Dark matter, making up about 27% of the universe's mass energy, doesn't emit, absorb, or reflect light. We know it exists only through its gravitational effects. Galaxies spin too fast to be held together by visible matter alone, and galaxy clusters bend light from background sources more than their visible mass can explain. The nature of dark matter remains unknown. Leading candidates include WIMPs, weakly interacting massive particles, and axions, exotic particles predicted by theory but never detected. Experiments around the world search for dark matter signals deep underground to avoid interference. Dark matter played a crucial role in the universe's evolution. Its gravity pulled ordinary matter into clumps that became the first galaxies. Without dark matter, galaxies wouldn't have formed, stars wouldn't have ignited, and time would have flowed through an empty, expanding universe, devoid of complexity or structure. In a sense, dark matter is the invisible scaffolding of cosmic time. In 2025, astronomers using the James Webb Space Telescope identified approximately 300 unusually bright candidates in the early universe, existing less than 500 million years after the Big Bang. These objects, discovered through infrared dropout analysis, appear brighter and more structured than existing models predicted. Some may be exceptionally active galaxies, forming stars at remarkable rates. Others, nicknamed little red dots for their distinctive appearance, might represent something entirely new, perhaps galaxies with hidden supermassive black holes, or a new class of cosmic object we're only beginning to understand. Current theories didn't predict objects this bright and massive forming so early. Yet, observations reveal them glowing like embers from the universe's dawn, inviting us to refine our understanding of how galaxies formed. Each discovery brings new questions about time's earliest chapters. Light has a speed limit, 186,282 miles per second in a vacuum. Nothing can travel faster. This limit is built into the fabric of space-time itself and has profound implications for time. As objects approach light speed, time dilates. It slows down relative to stationary observers. At 90% of light speed, time passes at about half its normal rate. At 99.9%, time crawls by at just a few percent of normal. If you could reach light speed, you can't, as it would require infinite energy. Time would stop entirely from your perspective. Photons, particles of light traveling at light speed, experience no passage of time at all. From a photon's point of view, emission and absorption happen instantaneously, regardless of how far it travels. Every photon from the Big Bang, from distant stars, from the screen you're looking at, exists in an eternal present, outside the flow of time entirely. The South Pole Telescope released unprecedented data in June 2025, surpassing even the Planck satellite's cosmic microwave background measurements in precision. These observations, combined with data from the Atacama Cosmology Telescope, confirm something puzzling. There's a persistent disagreement between different methods of measuring the universe's expansion rate. Observations of the early universe suggest one rate, while measurements of nearby supernovae suggest a faster rate. This Hubble tension has grown more significant with better data, not disappeared as expected. It might indicate that dark energy is changing over time, or that the universe's expansion history is more complex than current models predict. Some physicists speculate it could point to new physics, unknown particles or forces affecting cosmic evolution. Resolving this tension could reshape our understanding of time's march from the Big Bang to the present. Galaxies don't exist in isolation. They cluster together due to gravity, forming groups, clusters, and superclusters connected by vast filaments of dark matter and gas. The largest known structure, the Hercules Corona Borealis Great Wall, stretches across 10 billion light-years, containing billions of galaxies. Light takes 10 billion years to cross this structure, meaning we see different parts of it at vastly different cosmic times. When we observe the near edge, We're seeing galaxies as they were perhaps 7 billion years ago. The far edge appears as it was 14 billion years ago, closer to the Big Bang. No human brain can truly comprehend such scales. We can say the numbers, draw diagrams, but experiencing what it means, to see structure unfolding across 10 billion years of cosmic time, frozen in light, exceeds our intuitive grasp. Time becomes a landscape rather than a river. Neutrinos are ghostly particles that barely interact with matter. Trillions pass through your body every second, mostly from the sun, completely unnoticed. They travel at nearly the speed of light and have a tiny but non-zero mass. Neutrinos from the Big Bang still fill the universe, a cosmic neutrino background similar to the microwave background, but even harder to detect. These relic neutrinos, created when the universe was just 1 second old, have never been directly observed, but their effects on cosmic structure match theoretical predictions. In 2024, experiments measuring neutrino masses continued to tighten constraints, confirming that neutrinos are much lighter than other particles. Despite their faintness, neutrinos played a role in the early universe's evolution, affecting how matter clumped and galaxies formed. They are messengers from time's earliest accessible moment, flying through the cosmos at near light speed, mostly passing by unnoticed. The first galaxies were messy. Recent observations by the James Webb Space Telescope in 2025 revealed that early galaxies, forming 800 million to 1.5 billion years after the Big Bang, were chaotic and turbulent, rather than organized spirals. Researchers at Cambridge University studied over 250 young galaxies and found most were irregularly shaped, filled with dense clumps of gas and newborn stars, undergoing rapid bursts of star formation and frequent collisions with neighboring dwarf galaxies. Their internal motions were violent, with gas swirling at hundreds of kilometers per second. These findings challenge earlier assumptions that galaxies quickly settled into stable structures. Instead, the early universe was a time of cosmic adolescence, awkward, energetic, and constantly changing. Only later, as the universe aged and cooled, did galaxies calm down into the elegant spirals and ellipticals we see in our cosmic neighborhood today. Time's passage can be detected in starlight through a phenomenon called redshift. When a light source moves away from you, its light waves stretch, shifting toward the red end of the spectrum. The faster it recedes, the greater the redshift. Astronomers measure redshift using spectroscopy, identifying specific wavelengths emitted by elements like hydrogen and seeing how far they've shifted. A galaxy with a redshift of 1 appears as it was about 7.7 billion years ago. Redshift 6 corresponds to roughly 12.7 billion years ago, when the universe was less than 1 billion years old. The most distant object confirmed to date, observed by the James Webb Space Telescope in 2024, has a redshift of 14.32, seen just 290 million years after the Big Bang. These redshifts are time machines, showing us the universe at different ages, allowing us to witness cosmic evolution across billions of years. The arrow of time, the fact that time flows forward, not backward, remains one of physics' deepest mysteries. Physical laws are mostly time-symmetric. Equations work equally well, running forward or backward. Yet we experience time flowing only one direction. Cups shatter, but don't spontaneously reassemble. Eggs scramble but don't unscramble. We remember the past but not the future. The explanation involves entropy, a measure of disorder. The second law of thermodynamics states that entropy always increases in closed systems. The universe began in a state of very low entropy, highly ordered and uniform, and has been increasing in entropy ever since. Time's arrow points in the direction of increasing disorder. Why the universe started with low entropy is unknown. Some theories suggest it's related to the Big Bang's initial conditions, but no complete explanation exists. Time moves forward because the universe is moving toward increasing randomness and disorder. Gravitational waves are ripples in space-time itself, traveling at the speed of light. When massive objects like black holes or neutron stars spiral toward each other and merge, they shake space-time, sending waves outward. The first detection of gravitational waves in 2015 by the LIGO experiment opened a new window on the universe. Since then, over 100 gravitational wave events have been recorded, including mergers happening billions of years ago. These waves carry information about events that light cannot reveal, allowing us to hear the universe in a new way. In 2023, astronomers detected a background hum of gravitational waves pervading the cosmos, likely produced by countless black hole mergers throughout cosmic history. Time itself is not rigid, but vibrates with these passing waves, stretching and compressing space-time by tiny amounts as they pass, making the fabric of the universe ring like a bell. Supernovae, the explosive deaths of massive stars, serve as cosmic mile markers. Type 1, a supernovae, in particular, have a predictable brightness, making them standard candles for measuring cosmic distances. By comparing how bright they appear versus how bright they should be, astronomers calculate how far away they are. In the 1990s, observations of distant supernovae revealed that the universe's expansion is accelerating. Galaxies are flying apart faster now than in the past. This discovery was shocking and led to the concept of dark energy. These supernovae also mark time's passage, creating heavy elements that enrich space. When a massive star explodes, it forges gold, platinum, uranium, elements created only in these violent deaths and scattered into space. Future generations of stars incorporate these elements, planets form from them, and eventually, life uses them. Every atom heavier than iron in your body came from a supernova explosion, marking a moment in cosmic time. So, evidence builds from every direction. Distant galaxies reveal cosmic youth. The microwave background shows the infant universe. Atomic clocks measure time's flexibility. Gravitational waves ring through space-time. All of it points back to a singular beginning, time emerging from a state beyond our equations, beyond our experience, perhaps beyond our ability to fully understand. Yet here we are, creatures of time, living in these brief moments between the Big Bang and some far future ending. We measure, calculate, observe, and wonder. The universe allows us to see its history written in starlight, to feel its expansion pulling galaxies apart, to detect its oldest light fading into microwaves. Time began, yes, that much we know. But the deeper questions remain, hovering at the edges of knowledge, inviting us to look farther, think deeper, imagine beyond what current physics allows. Let yourself rest in that not knowing. You're still here, still drifting with us through these cosmic stories. Take a slow breath. Notice how your body feels a little lighter now, as if gravity itself has loosened its grip just slightly. We're traveling through space together, you and I and everyone listening in the quiet dark, floating through facts like asteroids drifting through the void. There's no rush, no destination, just the gentle momentum of curiosity carrying us forward. Let's continue. The cosmic web, the large-scale structure of the universe, resembles a neural network. Galaxies cluster along filaments of dark matter that stretch across hundreds of millions of light-years, connected by nodes where galaxy clusters form. Between these filaments lie vast voids, regions where few galaxies exist. This structure, formed over billions of years, as gravity pulled matter along the densest regions, creating a sponge-like pattern. Computer simulations of cosmic evolution reproduce this structure remarkably well, starting from tiny density fluctuations in the early universe and letting gravity work over time. The similarity to brain neurons or fungal networks is striking, though probably coincidental. The universe self-organized into this pattern through simple physical laws acting over vast timescales. Time's passage transformed a nearly uniform distribution of matter into a cosmos of beautiful complexity. If you could see all wavelengths of light, the universe would look different. Visible light shows stars and galaxies. Infrared reveals dust clouds and hidden star formation. X-rays expose hot gas and black holes. Radio waves trace magnetic fields and cold hydrogen. The James Webb Space Telescope observes primarily in infrared, allowing it to see through dust and detect the most distant galaxies whose light has redshifted into infrared wavelengths. In 2025, JWST captured images of galaxies so distant and faint that Hubble couldn't see them at all. These galaxies appear as they were in time's early chapters, less than 400 million years after the Big Bang. Each wavelength reveals a different aspect of cosmic history, a different layer of time preserved in light. Together, they build a complete picture of the universe's evolution from hot plasma to the rich tapestry of structure we inhabit. Quantum mechanics suggests that particles exist in superposition, multiple states at once, until observed. Schrödinger's famous thought experiment imagined a cat both alive and dead until someone looks. While that's an exaggeration, particles genuinely do behave this way. An electron can be in multiple locations simultaneously until measured. This quantum uncertainty extends even to time. Experiments have shown that events can exist in superposition of occurring at different times. In 2019, researchers demonstrated quantum time order superposition, where event A happens both before and after event B in a quantum sense. These effects are tiny, only measurable in carefully controlled experiments, but they hint that time at the quantum level is much stranger than our macroscopic experience suggests. Perhaps at the Planck scale, time itself exists in superposition, flickering between multiple configurations before collapsing into the steady flow we experience. The Milky Way, our home galaxy, contains about 200 to 400 billion stars. It's a barred spiral galaxy, meaning it has a central bar of stars with spiral arms extending outward. Our Sun is located about 26,000 light-years from the galactic center, in a minor spiral arm called the Orion Arm. The galaxy rotates, carrying the Sun and Earth around the center once every 225 million years, a cosmic year. Since Earth formed 4.5 billion years ago, we've completed about 20 orbits around the galaxy. Dinosaurs lived just one cosmic year ago. The galaxy itself formed about 13.6 billion years ago, shortly after the Big Bang. Time in the Milky Way is measured in these slow, majestic rotations. The stars we see tonight are not the ones our ancestors saw thousands of years ago. They've moved, shifted, changed position in their eternal dance around the galactic core. Black holes might be gateways to understanding time's ultimate nature. At a black hole's center lies a singularity, a point where density becomes infinite and space-time curvature breaks physics. Our equations produce nonsense, infinities that signal where our theories fail. Some physicists believe the singularity isn't real, that quantum gravity effects smooth it out into something else, maybe a wormhole to another region of space-time, or a bouncing point where a collapsing star spawns a new universe. Others think time ends at the singularity, literally ceases to exist. We can't observe inside black holes to find out. The event horizon hides everything beyond. But mathematical explorations continue. Solutions to Einstein's equations allow for exotic possibilities, white holes that expel matter, wormholes connecting distant regions, even time machines where loops in time become possible. These remain speculation, fascinating mathematics with unclear connections to reality. The observable universe has an edge defined by time, not space. Light from the Big Bang has been traveling for 13.8 billion years, but cosmic expansion means the most distant observable objects are now about 46.5 billion light-years away. This creates a sphere centered on Earth, our cosmic horizon. Beyond it lies more universe, perhaps infinitely more, forever hidden because light from those regions hasn't had time to reach us yet. As time passes, new regions come into view, but accelerating expansion means we're also losing others to darkness. Distant objects currently visible will eventually recede beyond our horizon, their light unable to bridge the growing gulf. In the far future, observers in our galaxy might see only their local group, isolated in expanding void, with no way to detect the broader cosmos that once surrounded them. Time might not be fundamental. Just as temperature emerges from molecular motion and isn't a basic property of matter, time might emerge from deeper quantum relationships. This idea, called emergent time, suggests that at the most basic level, the universe is timeless, with time arising only at larger scales from quantum entanglement or other processes. Research in quantum gravity, including loop quantum gravity and string theory, explores these possibilities. If time is emergent, the question what happened before the Big Bang transforms, there might be a more fundamental, timeless realm from which space-time crystallized. These are highly speculative ideas, debated among physicists, with no experimental evidence yet. But they remind us that our intuitive understanding of time, flowing like a river, absolute and universal, is likely incomplete, perhaps even misleading. Stars tell time through their lives. Massive stars burn hot and fast, lasting only millions of years before exploding. Medium stars like our Sun live about 10 billion years. The smallest red dwarfs can burn for trillions of years, far longer than the current age of the universe. By observing star populations in galaxies, astronomers can estimate ages. Globular clusters, ancient groups of stars orbiting galaxies, contain some of the oldest stars known, 13 billion years or more, formed shortly after the Big Bang. These ancient suns contain almost no heavy elements, confirming they formed before supernova enrichment occurred. White dwarfs, the cooling remnants of dead stars, also serve as clocks. They fade predictably over time, so their brightness indicates age. The oldest white dwarfs date to about 12.5 billion years ago. Stars are cosmic timepieces, marking the passage of ages through their birth, life, and death. Entropy, the measure of disorder, only increases. This is the second law of thermodynamics, one of the most fundamental principles in physics. A room gets messy, but doesn't spontaneously clean itself. Heat flows from hot to cold, never the reverse. Stars burn fuel, radiate energy, and cool. Eventually, in trillions upon trillions of years, the universe will reach maximum entropy. All stars will die. Black holes will evaporate through Hawking radiation, and everything will decay into a cold, dilute soup of particles at uniform temperature. This fate, called heat death, represents time's ultimate destination, a state where nothing changes and time becomes meaningless. No structure, no complexity, no life, just an infinite, dark expanse at a tiny fraction of a degree above absolute zero, with occasional random fluctuations the only events. This is, perhaps, how time ends, not with a bang but with an eternal, featureless stillness. Halfway through our journey now, we began at time's impossible start and followed it forward through plasma, through atomic formation, through the birth of stars and galaxies. We've seen time bend near black holes, measured in redshift, marked by radioactive decay. We've learned it's not absolute but flexible, not fundamental but perhaps emergent, not infinite but finite in both directions, a beginning at the Big Bang and an ending in heat death. Time is the stage for cosmic drama, yet also part of that drama, shaped by what happens within it. Physics describes time's behavior, but struggles to explain its essence. Why does it flow? Why does it have a direction? These remain mysteries. And in that mystery, perhaps, is where we find meaning, not in answers but in the asking, in wonder at the strange gift of consciousness moving through temporal moments, aware of itself, contemplating its place in the river. Let each breath guide you to realize time is yours, a separate stream that only you are living, while the vast universe continues to spin, expand, change. This second you're breathing, listening, is unique. Cherish the present moment, knowing that right now, your time is unique in the universe. And we continue drifting. The universe is not eternal. It had a beginning and will have an ending. This realization transformed cosmology in the 20th century. Before Hubble's observations, most scientists imagined a static, eternal cosmos. Now we know better. Time itself is finite, bounded by the Big Bang in the past and heat death in the incomprehensibly distant future. We exist in the middle chapters, when stars shine, galaxies evolve, and life emerges. This epoch, lasting perhaps 100 trillion years, is a brief flourish of complexity between initial simplicity and final simplicity. We are lucky, or perhaps necessary, to experience time during this active, creative phase, when the universe allows structures like stars, planets, and conscious minds to exist. Light preserves the past. When you look at Andromeda, our nearest large galaxy, you see light that left 2.5 million years ago. Human ancestors were just beginning to use stone tools. The light has been traveling through space all this time, a messenger carrying information across the void. Everything we see is history. The moon 1 second ago, the sun 8 minutes ago, distant stars centuries or millennia ago. We live surrounded by the past, preserved in light. The present moment is infinitely thin, always becoming history before we grasp it. Photons from the Big Bang still reach us, 13.8 billion-year-old light filling the sky. The universe is a living archive, every point in space receiving historical information from every other point, delayed by distance and the speed of light. Some ancient cultures believed in cyclical time, universes born, aging, dying, then born again in eternal recurrence. Modern physics explores similar ideas through cyclic cosmology models. The ekpyrotic universe proposes that our Big Bang was actually a collision between higher dimensional membranes in a pre-existing space. Conformal cyclic cosmology, suggested by physicist Roger Penrose, imagines each universe's far future evolving into conditions identical to another Big Bang. These models remain speculative, with little observational support. Yet they address a deep question: why should time begin at all? Cyclic models suggest it never truly began. It's been cycling eternally. Time becomes not a line with endpoints, but a circle, each ending seeding the next beginning, consciousness arising again and again in different cosmic epochs to ask the same eternal questions. The constants of nature, the speed of light, the gravitational constant, the strength of electromagnetic force appear fine-tuned for life. Change any slightly, and atoms couldn't form, stars wouldn't shine, or chemistry would be impossible. This observation has sparked debate. Some see it as evidence for design, others as statistical luck in a multiverse where every combination exists somewhere. But it also relates to time. These constants determine how fast processes occur, how long stars burn, how quickly complexity emerges. If gravity were stronger, stars would burn out too quickly for life to evolve. Weaker, and they'd never ignite. The constants set the tempo of cosmic time, the speed at which the universe moves from simplicity to complexity and back again. Life itself is a rebellion against entropy's increase. Living things create local pockets of order, complex molecules, organized cells, thinking brains, by consuming energy and exporting disorder to their surroundings. You maintain your structure by breaking down food, using its stored energy, and releasing waste heat. Locally, your entropy decreases, but globally, accounting for everything, entropy still rises. Life doesn't violate thermodynamics. It exploits temporary energy gradients. On Earth, sunlight provides the gradient. Stars fusing hydrogen provide the universe's energy flow. When stars die, energy sources dwindle, gradients flatten, and life's possibility fades. Time's arrow and life's arrow point together, both sustained by the universe's journey from low entropy to high, from order toward disorder, from useful energy toward waste. Time perception varies across species. A fly experiences time more slowly than we do. Its visual system processes more frames per second, making our movements seem sluggish. Dogs perceive time differently too, which is why they seem so excited when you return after minutes away. It felt longer to them. Humans experience time subjectively. Childhood summers felt endless, while adult years blur past. This isn't just memory, it's neural processing speed changing with age. But all biological time is measured by internal clocks, circadian rhythms, heartbeat rates, neural firing patterns. These clocks evolved to match Earth's rotation and orbit. Our experience of time is shaped by evolution, by neurons, by chemistry, not just by physics. Buddhism teaches that impermanence is fundamental. All things arise and pass away. Nothing endures. This ancient insight aligns remarkably with physics. Particles pop into existence, then vanish. Stars ignite and die. Even atoms eventually decay. Mountains erode. Species go extinct. Galaxies merge and transform. The universe itself is impermanent, emerging from the Big Bang and heading toward heat death. Clinging to permanence causes suffering because permanence is illusion. Time guarantees that everything changes. Nothing stays the same. Perhaps understanding time's flow helps us accept change rather than resist it, finding peace, not in permanence, but in the beauty of transient moments, each one unique and unrepeatable, precious, precisely because it passes. The Fermi paradox asks, if the universe is so vast and ancient, where is everyone? With billions of potentially habitable planets and billions of years for civilizations to arise, we should see evidence of alien intelligence, yet silence. Perhaps life is rarer than we think, or intelligence self-destructs, or we're early, the universe is still young, and most intelligence will emerge in the far future when long-lived red dwarfs illuminate their worlds. Or perhaps alien civilizations perceive time differently, existing on timescales too slow or fast for communication. A civilization that thinks in millennia might not recognize our brief radio signals as meaningful. Time might be a barrier between minds, as much as space is. Mathematics might be timeless, existing outside physical reality. The Pythagorean theorem was true before humans discovered it, before Earth formed. before the Big Bang. Mathematical truths seem eternal, not contingent on time or space. This raises strange questions. Does mathematics create the universe, or does the universe create mathematics? Some physicists believe reality is fundamentally mathematical. Space-time, particles, forces are all mathematical structures that happen to exist rather than merely describe existence. In this view, time itself might be mathematical, an axis in an abstract space where physical laws play out. Perhaps the universe is a mathematical object exploring its own implications, and we are temporary patterns within that exploration, equations becoming conscious long enough to contemplate themselves. Every photon emitted, every atom moved, every thought you think leaves a trace in the universe's information content. Where does this information go? Some physicists believe information is never truly destroyed. It might be preserved in quantum states, in the radiation escaping black holes, in correlations throughout space-time. The universe might be keeping a perfect record of everything that ever happened, encoded in ways we don't yet understand. In this view, the past never fully passes. It remains entangled with the present, preserved in the quantum substrate of reality. Your experiences, your choices, your existence, all permanently written into the universe's memory. A record time cannot erase, even as it flows forward. Could time restart? Some speculative theories propose that if the universe reaches maximum entropy, heat, death, perfect uniformity, quantum fluctuations might eventually, after incomprehensible eons, produce a new low-entropy state, a random fluctuation creating a small ordered region that inflates into a new universe. The waiting time would be staggering, 10 to the power of 10 to the power of 10 to the power of 56 years or more, numbers that dwarf the current age of our universe. But infinity is patient. Given infinite time, even impossibly rare events become inevitable. Perhaps our universe is already a fluctuation from a previous heat death. Time cycling not smoothly, but through vast deserts of nothing, punctuated by brief oases of existence, consciousness emerging rarely to experience brief moments before sinking back into eternal stillness. The moment you're experiencing right now exists simultaneously with the Big Bang, with dinosaurs, with the far future, all laid out in the four-dimensional structure of space-time. This is the block universe view, where past, present, and future all exist equally. Nothing ever truly passes. It just is, eternally present in space-time's structure. Time's flow is illusion, created by consciousness moving through the block, like reading a book page by page, even though all pages exist together. In this view, every moment of your life exists forever in space-time, forever present, forever real. You've already died and been born, simultaneously. Time doesn't flow, you do, along a path through unchanging space-time. Quantum entanglement links particles across space instantaneously. Change one, the other changes too, no matter the distance. Einstein called it spooky action at a distance. Recent experiments confirm entanglement is real, though no information travels faster than light. But entanglement also occurs across time. A particle measured today can be entangled with a particle measured yesterday or tomorrow, linking past and future in quantum correlations. This temporal entanglement suggests time might not be as separated into distinct moments as we think. Past, present, and future might be quantum mechanically connected, influencing each other in ways classical physics never imagined. Time, at the quantum level, refuses to stay in neat boxes. The sun will die in about 5 billion years, swelling into a red giant that engulfs Earth's orbit. Long before then, in roughly 1 billion years, increasing solar output will boil Earth's oceans and end all life. Humanity has existed for perhaps 300,000 years, an eye blink in cosmic time. If we represent the universe's age as a calendar year, human civilization appeared in the last few seconds of December 31st. All of recorded history fits in the final fraction of the final second. Yet we're conscious, we wonder, we seek meaning. Our brief flicker of awareness against vast temporal darkness is either cosmically insignificant or the whole point, consciousness giving the universe a way to know itself. Time travel to the future is possible. We do it by moving fast or experiencing strong gravity. An astronaut traveling at near light speed for a year might return to find decades passed on Earth. Near a black hole, hours might equal years elsewhere. But backward time travel faces problems. Paradoxes arise. If you prevent your own birth, how did you exist to travel back? Some mathematical solutions to Einstein's equations theoretically permit closed time-like curves, loops in space-time that would, in principle, allow backward time travel. However, such solutions require exotic conditions like rotating black holes or traversable wormholes, which may not exist in our universe. Physical laws, particularly quantum mechanics, might prevent paradoxes through mechanisms we don't yet fully understand. Time travel to the past remains a fascinating mathematical possibility without clear pathways to physical reality. Memory is time's shadow. Without memory, you'd have no sense of duration, no past, only an eternal now. Memory creates continuity, the feeling that the you of this moment connects to the you of yesterday. But memory is unreliable, reconstructed each time you recall it, subtly changing. You don't remember the past. You remember the last time you remembered it. Your timeline is constantly being rewritten by neural processes. In a sense, your personal time is what your brain constructs, not what objectively happened. Time, for consciousness, might be more like a story we tell ourselves, coherent, continuous, but partly fictional, shaped by forgetting and invention, as much as by truth. Ancient astronomers noticed patterns, seasons, lunar phases, star positions cycling predictably. They built calendars, marking time's passage with increasing precision. Sundials tracked shadows, water clocks measured flow, mechanical clocks ticked in cathedrals. Now, atomic clocks measure time, using cesium atoms vibrating 9,192,631,770 times per second, defining the second with extraordinary precision. Time has become a technology, something we measure and control, yet what we're measuring remains mysterious. Clocks track changes, cycles, processes, but is time those processes or something underlying them? Do clocks measure time, or do they create it through their rhythmic motion? Perhaps time is nothing more than what clocks measure, a circular definition, revealing our confusion about time's fundamental nature. The cosmic microwave background is our baby picture, showing the universe at 380,000 years old. It appears uniform in all directions, with tiny temperature variations, mere thousandths of a degree, encoding information about early density fluctuations. These fluctuations grew under gravity into galaxies. In a real sense, the pattern of temperature variations in the ancient sky predicted where you would be born billions of years later. Your existence was encoded in quantum fluctuations during inflation, frozen into the cosmic microwave background, then amplified by gravity over eons until solar systems formed and life emerged. You are the universe's early conditions playing out. A ripple from the Big Bang made conscious, time becoming aware of itself. Some philosophers argue time is unreal, an illusion created by consciousness. In the equations of fundamental physics, time is just another dimension like space. You can run equations forward or backward. They work either way. Nothing in physics requires time to flow. The now, the feeling of present moment, appears nowhere in equations. Yet our experience insists time flows, that past differs from future, that now is special. Maybe consciousness creates time. Maybe we impose temporal order on a timeless reality, our brains constructing flow from static four-dimensional structure. Or maybe time is real and fundamental, and physics has simply failed to capture its essence. The mystery persists, irreducible. Stars are nuclear furnaces, converting mass to energy via E equals mc squared. This equation, Einstein's most famous, links mass and energy through the speed of light squared, a huge number, meaning tiny mass becomes enormous energy. The Sun converts 4 million tons of mass to energy every second, yet has enough fuel for billions of years. This stellar alchemy creates time's structure. Without nuclear fusion, stars wouldn't shine, planets wouldn't warm, life wouldn't emerge. The universe would be cold and dark, expanding but lifeless. Time would still exist in some abstract sense, but there would be no clocks, no processes, no observers. Consciousness needs stars, and stars are possible only because mass and energy interchange through light's speed. Galaxies collide, a slow-motion dance spanning millions of years. The Milky Way and Andromeda will merge in about 4 billion years, their stars passing harmlessly between each other. Space is so vast that collisions between actual stars are unlikely, but gravitational interactions will reshape both galaxies, flinging stars into new orbits, triggering bursts of star formation as gas clouds compress. Eventually, they'll form a single elliptical galaxy, sometimes called Milkomeda. Time will witness this grand restructuring. Solar systems redistributed, new stars born from old gas, black holes at each galaxy's center, spiraling together and merging. Cosmic time operates on scales where galaxies themselves are transient structures, endlessly combining and transforming. Your body carries ancient history in every cell. The water you drink is billions of years old, cycling through clouds, rivers, and bodies since Earth formed. Your DNA carries information refined over 4 billion years of evolution, instructions written in the language of base pairs, edited by natural selection across countless generations. The genetic code in your cells connects you to every living thing on Earth. Plants, bacteria, whales, all sharing common ancestry. You breathe oxygen, created by ancient cyanobacteria 2.4 billion years ago. Time flows through you, using your atoms to briefly form a pattern that thinks and feels before releasing them to form other patterns. You are time's temporary expression, a moment of self-awareness in matter's long journey. In the far future, assuming humanity survives, we might become unrecognizable. Evolution continues. We're not evolution's endpoint, but another step. Our descendants might be biological, technological, or some merger of both, spreading through the galaxy over millions of years, adapting to different worlds. Their experience of time might differ from ours. Uploads to computers might think at digital speeds, experiencing centuries in subjective minutes, or they might slow down, living at geological pace, thinking one thought per millennium. Time's subjective experience is not fixed, but depends on the physical substrate of consciousness. Future minds might experience time in ways we literally cannot imagine, as different from our experience as ours is from a bacterium's. The universe could have been different. The laws of physics, the constants of nature, even time's existence aren't necessary. They just are. We don't know why these laws, and not others, why this universe, and not nothing. Physicists search for a theory of everything, explaining why reality has its particular form, but such a theory might itself rest on arbitrary assumptions. Perhaps reality is fundamentally arbitrary, contingent, without deeper explanation. Or perhaps there are infinite universes with different laws, and we're in one where laws permit consciousness to ask why. The mystery of existence, the question of why there is something rather than nothing, remains unanswered. Time itself is part of that mystery, as inexplicable as anything. We now understand, through countless observations and experiments, that time began with the Big Bang and will end, or at least become meaningless, in heat death. Time is relative, flexible, curved by gravity. It flows from past to future, carried by entropy's increase. It emerges from quantum processes, or maybe is fundamental. It is measured by clocks, but experienced by consciousness. It allows change, enables cause and effect, makes stories possible. Without time, nothing would happen. The universe would be a frozen, unchanging block. Time gifts us with moments, with experiences, with the possibility of growth and understanding. It is perhaps the universe's greatest gift to consciousness. Let that thought rest gently now, as we drift deeper into stillness. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. Spacecraft orbit Earth. Earth orbits the Sunday. The Sun orbits the center of the Milky Way. All are circles, cycles, endless orbits. Like your breath, inhale, exhale, inhale, exhale. A small cycle within the vast universe. You are also part of that eternal movement. You don't need to hold on to anything. Let everything unfold in its perfect order, like planets silently rotating in their orbits, unhurried, unresisting, simply existing. We're almost there now. So how did time begin? With quantum uncertainty becoming cosmic inflation, with symmetry breaking into complexity, with nothing, or something we cannot name, transforming into space-time itself. The mechanics are mathematical, beautiful in their precision, but the reason? That remains beyond us. Perhaps there is no reason, only the fact of existence. Or perhaps the reason is so far beyond our thinking that asking is like asking an ant to explain relativity. We don't know, and that's okay. Time teaches patience. Stars take millions of years to form. Mountains rise grain by grain. Evolution works through countless generations. Tiny changes accumulating over eons. Nothing cosmic happens quickly. The universe doesn't rush. It has all the time, literally. We humans hurry through our brief decades, but we're embedded in a universe that operates on scales that make our urgency seem almost comical. Perhaps learning to think on cosmic timescales brings peace, accepting that some things simply take time, cannot be rushed, must unfold at their own pace. The universe will outlast everything we build, everything we know, everything we care about. In 10 to the power of 100 years, a 1 followed by 100 zeros, even black holes will have evaporated. The universe will be dark, cold, nearly empty. All structure will have dissolved. Yet right now, for this brief cosmic moment, stars shine, planets orbit, life thrives, consciousness looks up at the night sky and wonders. We exist during the universe's golden age, when time still allows for complexity and beauty. That makes this era special, precious, unrepeatable. Time is a gift we didn't ask for but have anyway. You didn't choose to exist, to be born into time's flow, yet here you are, a temporary arrangement of particles experiencing moments, feeling emotions, thinking thoughts. For a brief while, the universe organized itself into you, gave you time, a span of years to live, learn, love, wonder. Then your time ends. Your atoms scatter, but they remain part of the universe, eventually becoming other patterns, other beings, other moments of awareness. Every civilization that ever exists will face time's mystery. Aliens on distant worlds. If they exist, look up at their skies and see ancient light. Wonder about origins. Puzzle over time's nature. The question, how did it begin, might be universal, asked by every conscious mind emerging in this cosmos. We share that question across space and time with all thinking beings. It connects us to a community of questioners, minds separated by distance but united by wonder, all contemplating the same cosmic mystery. Time is measured by change. If nothing changed, time would be meaningless. A universe frozen, static, unchanging, has no time, or time without meaning. Change creates time, and time allows change. They're inseparable. Your experience of time passing is really the experience of neurons firing, thoughts arising, sensations shifting. Even sitting still, your mind changes, and you feel time. The universe likewise. Particles move, fields fluctuate, entropy increases. Time and change dance together, neither leading, both essential to the cosmos we inhabit. Ancient humans watched sunrises and sunsets, marking days. They noticed lunar phases, marking months, seasonal cycles, marking years. They built stone circles, aligning with solstices, tracking time's passage with remarkable accuracy. These monuments still stand. Stonehenge, Newgrange, countless others, testaments to humanity's long relationship with time. We've always been timekeepers, pattern seekers, trying to understand the rhythms governing our lives. That impulse connects us to our ancestors across millennia. We share the same sky, the same cycles, the same questions about time's nature. Light from the Big Bang has been traveling for 13.8 billion years. In that time, it has covered incomprehensible distance, stretched by expansion, cooled to microwave wavelengths, carrying its message through the void. And now it arrives here, detected by telescopes, analyzed by scientists, contemplated by you as you lie here listening. Time connects that ancient moment to this present one. You are the destination of that light's long journey, a point in space-time where the universe becomes aware of its own history. Sleep itself is a journey through time. You close your eyes, consciousness fades, hours pass in what seems like moments. You wake in a future you didn't experience, having jumped forward while your body rested and repaired. Every night you practice a small death and rebirth, dissolving into unconsciousness and emerging renewed. Sleep is time travel, skipping forward through the darkness, arriving in tomorrow without experiencing the transition. It's a daily reminder that consciousness is intermittent, not continuous, flickering on and off. The present moment is all you ever have. Past is memory. Future is imagination. Only now exists. This immediate experience of being alive, aware, breathing. Yet now is infinitesimally thin, always becoming past before you grasp it. Try to hold the present. It's already gone, replaced by new now. Time is paradoxical. You live only in the present, yet the present never stays. It flows constantly, unavoidably, carrying you forward whether you want to go or not. Perhaps peace comes from accepting this flow. Clocks don't create time, they track it, or do they? Perhaps time is nothing more than what clocks measure. Without change, without cycles, without measurement, would time exist? This is philosophy veering into mystery. Does time exist independently of things happening in it, or is time simply the word we give to the fact that things happen in sequence? No one knows for sure. Time might be fundamental, or emergent, or illusion. After all our science, the basic question remains, what is time really? You are time's child, born from its flow. Your parents existed in time before you, their parents before them, lineage stretching back through history, through prehistory, through evolutionary ages to the first organisms. Those organisms formed from chemicals that gathered over time. Those chemicals formed from atoms forged in stars that lived and died over billions of years. The atoms came from the Big Bang. You are time made flesh. The universe's long history embodied in one temporary form, conscious for a while before dissolving back. Time gives meaning to choice. If everything were predetermined, unchangeable, your choices wouldn't matter. But time flows forward with genuine uncertainty, quantum randomness, chaos, free will perhaps. You make decisions that shape your future, create moments that become your past. Time allows agency, the possibility that your actions matter, that you can affect what comes next. Without time's flow, without cause preceding effect, without the open future, existence would be meaningless. Time creates meaning by allowing genuine becoming, real change, true novelty. The stars you see tonight will still be shining long after you're gone. Your brief life fits within cosmic time like a single heartbeat. This could seem depressing, your cosmic insignificance. Or it could seem liberating. You're part of something vast and ancient, connected to the whole universe. Your atoms are star stuff, your existence made possible by cosmic history stretching back to time's beginning. You are not separate from the universe, but embedded in it, made of it, a way for it to experience itself briefly. Time heals, they say, and perhaps it's true. Wounds close, grief fades, difficult memories lose their sting. Time changes us whether we want it to or not. You are not the same person you were 10 years ago. Your cells have replaced themselves. Your memories have changed. Your mind has grown. Time is transformation, constant becoming, never staying still. You cannot step in the same river twice, said Heraclitus, because the river changes and so do you. Time ensures nothing remains the same, including yourself. In dreams, time behaves strangely. Events that seem to last hours occur in minutes. You can visit the past, see the future, jump between moments without transition. Time's normal rules suspend. Some theorists suggest dreams are how brains process information, consolidate memories, explore possibilities. Others wonder if dreams hint at time's deeper nature. Perhaps time's linearity is constructed by waking consciousness, and dreams show time's true, non-linear character. Or perhaps dreams are simply neural noise, meaningless firing patterns we try to interpret as story. Music exists in time. A melody unfolds moment by moment, notes following each other in sequence. You can't hear a symphony all at once. It requires time to experience. Beauty often needs time. Stories need beginnings, middles, ends. Dances need motion. Conversations need turn-taking. Time allows art, narrative, meaning to emerge from sequence. Without time's flow, there'd be no music, no stories, no becoming. Time is the canvas on which beauty is painted. Appreciating art means surrendering to time's flow, following where the music leads. Time eventually returns all patterns to the universe. Cells change, energy redistributes, and the atoms that form you continue their cosmic journey. Entropy increases, processes slow, organs transform. This fact can terrify or motivate. Some find meaning in mortality. If life were infinite, would moments matter? Scarcity creates value. Your limited time makes each moment precious. Some find comfort in transformation. You'll return to the universe. Your atoms recycled, your energy redistributed. You came from cosmic processes and returned to them. Time gave you life temporarily, then reclaims you for new patterns, new forms, new expressions of existence. Children experience time slowly. Summers last forever. Waits are interminable. Adults feel time accelerate, years blur past. This isn't imagination, it's perception. As you age, each year becomes a smaller fraction of your total life. At age 5, 1 year is 20% of your existence. At 50, it's 2%. Subjectively, years seem shorter because they represent less of your lived experience. Time's passage feels faster as you age, not because time changes, but because you do, accumulating more past against which to measure the present. Love exists in time. Relationships develop over months and years, trust building, intimacy deepening, shared experiences accumulating. You cannot instant love someone. It requires time together, memories created jointly. Love is partly those memories, that history, the time you've invested in another person. And love fears time, aging, change, eventual loss. Mortality shadows every relationship, yet time also makes love possible, beautiful, meaningful. The temporary nature of connection gives it poignancy. You love someone, knowing time is finite, making every moment together precious. The universe doesn't care about you. That sounds harsh, but it's liberating. Cosmic time marches on indifferent to your struggles, your hopes, your fears. Stars explode, galaxies collide. Entropy increases whether you're happy or sad, successful or failing. This indifference frees you. You're not the center. Your problems aren't cosmic tragedies. Your existence doesn't require universe-level justification. You simply are, briefly, one small pattern of consciousness in vast space-time. That's enough. You don't need to be important cosmically to matter to yourself and those you love. Time allows forgiveness. Mistakes recede into the past, sharp edges softening with distance. You can choose to let go, to stop carrying old hurts forward through time. Not forgetting, the past remains, but releasing its grip on your present. Time creates space between then and now. Space where healing happens, where new possibilities emerge. Yesterday's pain doesn't have to define today. Time offers that gift, separation from the past. However slowly, you can change, grow, become someone new. Time permits transformation. Right now, as you listen, time flows through you. Blood circulates, neurons fire, cells divide, breath enters and leaves. You are time in action, processes unfolding, change happening. You're not a static thing but an event, a temporary pattern of ongoing processes. You are really a verb, not a noun, a doing, not a being. You are happening right now, this moment, existing as time flows through the space you occupy. When time stops flowing through this pattern, you ends, the processes cease. Gratitude might be the right response to time. You didn't create yourself, didn't earn existence, yet here you are, gifted time, given moments, granted awareness. The universe didn't have to become conscious, didn't have to produce beings who could appreciate beauty, understand physics, feel love, yet it did. Time brought forth complexity. Complexity brought forth life. Life brought forth minds. And now you're here, aware, experiencing this moment. Perhaps simply saying thank you to existence itself is enough. Thank you for time, for awareness, for this moment of being. Time flows, you flow with it. From the Big Bang to this moment, through every instant of cosmic history, the river has carried matter and energy toward this exact configuration. You, here, now, conscious, aware, breathing. The universe made time so that stars could form, so that planets could cool, so that life could emerge, so that minds could wonder about their origins. Or perhaps, those are just patterns we impose on randomness. Either way, Time brought you here, to this quiet moment, where past and future meet in the thin edge of now. Rest in that edge, let time carry you gently into sleep. And so, our quiet journey through time's mystery comes to a gentle close. We've traveled from quantum foams smaller than atoms to cosmic horizons billions of light years wide, discovering along the way that time is not what it seems, not absolute, not separate from space, perhaps not even fundamental. From the Planck epoch's impossible heat to the cold emptiness of far future heat death, we've glimpsed how time began, flows, and will someday end, or transform, or cycle. We don't know. Time reminds us that everything changes, nothing lasts, and impermanence is woven into reality's fabric. Much of the profound truth about existence happens in mathematics and physics, too abstract for words. Yet time also gives us this gift, the present moment, always available, always new, where conscious experience unfolds. By pausing to notice, we glimpse the extraordinary, that we exist at all in this epoch when stars shine, during this brief flourishing between cosmic dawn and cosmic twilight. And now, in these final minutes, take the deepest breath you can, as deep as possible. Think about unity, of every atom, every event, every moment in the universe. You are not separate. You are a link in the endless chain. Think about the unity of every atom in a black hole, where all boundaries dissolve, light, matter, time, all becoming one. You too can dissolve into sleep like that. No boundaries left between you and rest. Let your entire being dissolve into the gentle darkness, into the soft gravity pulling you into sleep. If this gentle journey through time brought you peace tonight, perhaps share it softly with someone else who's searching for stillness under the stars. It might be exactly what another restless mind needs to finally let go and drift. One quiet share, one peaceful night at a time. But there's no need to do anything now, nothing at all. You've traveled far tonight, farther than most journeys take you. You can allow these thoughts of time and cosmos to fade now, like stars disappearing into dawn light, leaving only peaceful calm behind. Let your breathing deepen. Let your body feel heavier, as if Earth's gentle gravity is pulling you safely down into rest. If sleep comes, let it carry you like a wave onto shore, smoothly, inevitably, into a realm where time and weight no longer matter. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, the universe will still be expanding. Stars will still be shining. Time will still be flowing through space-time. But tonight belongs to stillness. Rest well, cosmic traveler. And remember, time began so you could exist. Fall asleep to gentle facts. Where science meets sleep, dream deeper with bedtime science. Relax, listen, and drift into sleep. Good night.